Heat flow. In almost any chemical process plant, materials are constantly being heated or cooled. This is done for a variety of reasons. As we have seen in previous unit, it is often necessary to heat viscous material in order to make them flow easily. Another reason for heating is to melt solid or to change liquid into vapors by boiling them. Chemicals may be heated to increase the span of a chemical reaction or to make it occur at all. A handy rule known to most chemical engineers is that a 10 degrees Celsius increase in temperature will approximately double the rate of most reactions, but some chemical reactions give off heat as they occur. Such materials generally require cooling if the reaction is to be properly controlled. Cooling is also required to change or to condense vapors into liquid and to freeze liquid into solid. In many reactions, the temperature influences the product being formed. Consequently, the temperature must be controlled so that the materials remain at the temperatures that produce the highest yield of the most desired product. The science is concerned with the generation of transfer of heat is called thermodynamic. The subject is emphasized in every chemical engineer's education. The science of thermodynamics was developed in the 15th century as a result of the need to describe the basic operating principles of the newly invented steam engine and to provide a basis for relating to work produced to the heat supplied. Thus, the name itself denotes power generated from heat. From the study of steam engines, the emerged two of the primary generalization of science, the first and second law of thermodynamics. All of classical thermodynamics is implicit in this law. Their statements are very simple, but their implications are profound. The first law simple says that energy is conserved, meaning that it is neither created nor destroyed. It provides no definition of energy that is both general and precise. No helps come from it is common informal use where the word has imprecise meaning. However, it is scientific or engineer's context. Energy is recognized as appearing in various forms, useful because its form has mathematical definition as a function of recognizable and measurable characteristic of the real world. Thus, kinetic energy is defined as function of velocity and gravitational potential energy as a function of elevation. The second law is difficult to comprehend because it depends on entropy, a word and concept not in everyday use. Its consequences in daily life are significant with respect to environmental conservation and efficient use of energy. Formal treatment is postponed until we have laid a proper foundation. In almost all chemical process plants, heat is generated by burning of fossil fuel, coal, oil, or natural gas. The heat given off by the burning fuel might be used directly, but most often it is used to generate steam, which is piped to places where heat is needed. Furthermore, the second law of thermodynamics is a powerful tool for all design, optimization, and performance evaluation of thermal systems. The easiest way of heating a liquid with steam is to bubble the steam directly into the liquid. For example, steam can be supplied to a pipe immersed in the liquid. A number of small holes are drilled in the pipe to allow the steam to escape in small bubbles. Such as device is called sparger. The bubble of steam rise up, transferring heat to liquid and mixing in the same time. During the process, some or all of the steam condenses into water, which remain in the liquid being heated. Consequently, this is kind of heating called direct injection of steam can be used only if the pressure of condensed water is not a problem. In most cases, direct injection of steam is impossible. The steam and the liquid to be heated must be kept separate. To heat the liquid without direct contact, a piece of equipment called a heat exchanger is used. It has a barrier of some solid material between the heating medium and the material to be heated. Many varieties have been invented, but by far the most common type is the cell and tube heat exchanger. The material to be heated may be tube side or pass through to the tubes, with the steam cell side or outside the tubes. It is impossible to have steam on the top side or the material on the cell side, but this is uncommon. Usually the steam is on the cell side, so that is condensed on the outside of the tubes. The resulting water falls to the bottom of the cell, whereas it is allowed to pass out of the heat exchanger by means of a special device called a steam trap. This is designed to permit the escape of condensate or water content from the steam, while trapping the steam or preventing it from escaping. At normal atmosphere pressure, water boils at 2012 degrees Fahrenheit or 100 degrees Celsius, and it is steam is at the same temperature. If the pressure is increased, the boiling point of the water and the temperature of the steam being produced or rise. To use high temperature steam, it is necessary to design a breadth of equipment to withstand the high pressure associated with the high temperatures. High pressure equipment is expensive. Sometimes to provide high temperature without having to deal with high pressure, chemical engineers use special heat transfer liquid for heating. There are materials that remain liquid at much higher temperature than water. Two common heat transfer liquids are known as Downstream A and Downstream A. Downstream is a trademark of the Dow Chemical Company, which manufactures and markets the product. Downstream A is a mixture of two chemicals, differently and deeply oxidized. It boils at 450 degrees Fahrenheit. Downstream A is dichlorobenzene, which boils at about 300 degrees Fahrenheit. Some mineral oil are also sold for use as heat transfer liquid at temperatures ranging about 600 degrees Fahrenheit, but most of them is deteriorated if kept at high temperatures for a long time. If a material is to be cooled, a cell and tap heat exchanger can also be used. The cooling medium is normally water, chilled water, or cold brine. As mentioned earlier, brine is used because it freezes at lower temperature than pure water. Sometimes liquids are cooled by circulation them through space exposed to the atmosphere. This is called an air-cooled heat exchanger. The cooling process is speed if a fan is used to blow cool air rapidly over the taps. When a cell and tap heat exchanger is used for cooling, the material to be cooled may be either on the tube side or cell side, with the cooling medium on the other side. If one of the two liquids is more corrosive than the other, brain, for example, can be corrosive. It is usually on the top side. The tops can then be made of a corrosion-resistant material with a cheaper material from the shell. If a corrosion material is used on the shell side, it contacts with both the inner surface of the shell and outer surface of the tops. Both the tops and shell must be able to withstand corrosion. It is possible to operate shell and top heat exchanger is either the horizontal and vertical position, but horizontal exchanger are most common. When steam is used for heating, it is always introduced through the upper opening or nozzle in the shell so that the lower opening can be used for draining condensate. If a pool of condensate built up in such as exchanger, usually due to a malfunctioning or wrongly sized steam trap, and submerge some of the taps, the heat transfer suffers because condensing steam transfer heat more rapidly than the hot water. When a liquid is used on the shell side, it is always introduced through the lower nozzle in withdraw through in upper nozzle. In this way, the engineers can be assured the exchanger remains full with liquid surrounding all the taps. Shell and top heat exchanger are widely used that they are available as stock items for many manufacturers. There are a number of standard designs used throughout the industry. There is detail of publication of the Tubular Exchanger Manufacturer Association and are therefore called TEMA standard. However, no group of standard exchanger could fulfill all needs, so many exchangers are custom designed all manufactured. The size of the shell and top heat exchanger needed for any particular job needs mainly the amount of heat to transfer and the volume of liquid to be handled. The calculations are learned in college by most chemical engineers by computer programs doing them automatically. Although most heating is done with steam or heated transfer liquid such as downtrim, another liquid may also be used as the heating medium. This is most commonly done when there is one liquid stream in plant that needs to be heated or another needs to be cooled. Passing both streams through the steam heat exchanger will accomplish both objectives simultaneously. When a heat exchanger is used with the liquid on both the top side and the shell side, then the liquids are usually made to flow in opposite direction. This is known as countercurrent flow. If both materials flow in the same direction, its flow is called concurrent. Sometimes a heat exchanger is designed to chill the vapors of a substance and condense it into a liquid. A special exchanger of the kind is called condenser because of the way it is used. Although it is not too difficult from any other exchanger, when used as considered, shell and top heat exchangers are often mounted vertically. When a liquid flows in a pipe, it moves fastest at the center of the pipe and slowest at the wall because of friction between the pipe and the flowing fluid. When fluid flows relatively slowly, there can be a fairly thick layer of liquid near the pipe wall that hardly moves at all. This condition is known as laminar flow and makes for poor heat transfer because the static layer of fluid near the wall acts as resistance to movement of heat. When fluid is flowing rapidly, swirls and eddies are set up that reduce the thickness of static layers. near the pipe well, and there be decrease the resistance to movement of heat, or increase the rate of heat transfer. This kind of agitated flow is known as turbulent flow. The speed at which laminar flow changes to turbulent flow was investigated early in this century by a experimenter named Osborne Reynolds. He works out of a relationship known as Reynolds number that helps to determine the transmission from laminar to turbulent flow. The Reynolds number is found by multiplying the inside diameter of pipe by the fluid velocity and fluid density, and then dividing by the fluid viscosity. The unit used for the variable are selected so that all the units shell out. Hence, and Reynolds number is known as dimensionless number. For example, diameter in centimeter, velocity in centimeter per second, density in grams per cubic centimeter, and viscosity in gram per centimeter second. When the Reynolds number is less than 2.1, flow is always linear. When it is above 4, flow is always turbulent. Between Reynolds number of 2.1 and 4, the flow may be either linear or turbulent, depending on condition at the entrance of the pipe or the distance downstream from the entrance.